Hi everyone, this is 10.7 probability. So there's quite a bit of vocabulary up front on this particular lesson, so I'm going to kind of show you guys everything you need, and you certainly can pause and write if you need to, but I'm going to talk through these definitions as we work. The first one we have is empirical probability. These are situations where we observe how frequently an event occurs in a given number of trials or observed incidents. The big idea here is there's some experiment that's going on, right? Any occurrence for which the outcome is uncertain. Basically, our probability, our empirical probability, will be the observed occurrences of some event E divided by the total number of observed occurrences. So if we had some experiment where we were tracking to see how many birds flew over a certain area that were blackbirds, we would say, well, we would observe the total number of blackbirds and the total number of birds that flew, and dividing the total number of blackbirds by the total number of birds would give us the probability that the next bird that flew by would be black. The sample space is what we define as the set of all possible outcomes. And a specific event is a subset of the sample space, one outcome that we are looking for. More common when we talk about probability is theoretical probability, situations where the sample space only contains equally likely outcomes, such as a coin toss or a roll of a dice. We don't actually need trials, we don't actually need an experiment in order to make sense of the probability. But again, this probability will be found by taking the number of outcomes in an event that we are looking at divided by the number of total outcomes in the sample space. If we were to take a roll of the dice, and I was trying to find the probability of a 2, well, there is only 1 2 out of 6 equally likely outcomes, so our probability would be 1/6. So what we know about theoretical probability is that the probability of one of the possible events happening is 1, right? So the sum of the theoretical probabilities of all possible outcomes is 1. So this is useful when we're dealing with something like the probability that a certain event won't occur. Sometimes it's easier to think about the probability of something not happening rather than the likelihood of the opposite happening. So what we can do instead is rewrite it as 1 minus the probability some event does occur. So if, just to use an example, the probability of pulling the ace of spades from a deck of cards would be 1 out of 52. The probability of not the ace of spades would be 1 minus 1 over 52, or 51 out of 52. Rather than adding up all the cards that are not an ace of spades, I can just simply say, well, I know that the probability of getting the ace of spades would be 1 out of 52. Everything else, 1 minus 1 out of 52, would get me my probability that I don't get that ace of spades. There's some other definitions here that we need to get comfortable with. First is the idea of mutually exclusive events, two events that cannot occur simultaneously. Think about this as rolling a 2 and a 3 on a dice, right? They can't do both of them at the same time. What we do is we add their probabilities together, right? So in that dice example, it would be 1 out of 6 to roll a 2 and 1 out of 6 to roll a 3. So it would be 1 out of 3 to get 2 or 3. Non-mutually exclusive events are events that can occur simultaneously. In order to find their probability, I find the likelihood that both happen, right? Probability of A and B, the probability of A and the probability of B, but then I subtract them both happening. I think the easiest way to think about this is a Venn diagram. So say I have two situations that are mutually exclusive, non-mutually exclusive. Non-mutual exclusive. Well, the likelihood that event A happens is here in red. And the likelihood that event B happens is here in blue. Now, what you may have noticed is that this middle section is both red and blue. So let's say this were A and this were B. If I wanted to find the probability of these non-mutually exclusive events, I would take the probability of A plus the probability of B. But in that process, I've double counted this section in the middle, right? This section that's now in green. So what I do is I subtract that middle section. I subtract the probability of A and B happening simultaneously. So when I have non-mutually exclusive events, I need to account for the fact that by adding, I may have double counted certain elements. We also have independent and dependent events. Independent events we can think about as events that occur one after another, and independent events don't affect one another, whereas dependent events do. Independent events we can think about rolling a dice, picking it up, and rolling it again. It doesn't matter what I roll on the first dice, the probabilities are unchanged when I roll that dice a second time. Now, when it comes to dependent events, they do affect one another. The way we find this is we take the probability of the first event happening and multiply it times the probability that the second event happened given the first one already has. So we can think about this example as picking cards from a deck. Let's say I wanted to find the probability of an ace and then another ace. Well, the probability of pulling an ace would be 1 out of 13. A probability of pulling an ace and then another ace, sorry, that should be 1 over 13, would be 1 over 13 for the first ace, and then 3 out of 51, the probability that I pull that second ace, given that I've already removed one ace from the deck. So these are all a bunch of vocab, and a lot of what we do in this unit is going to be basically figuring out what situation we have and trying to make sense of it. So now that we have our vocab out of the way, I'm going to move back over to our examples in our clean notes. So here on example 1, they tell us that we have a jar containing white, blue, and orange marbles. The probability of selecting a marble that is white, probability of a white marble is 1 out of 3. The probability of a blue marble is 1 out of 4. We are trying to find the probability of orange. Well, we know that those are the only options we have, white, blue, and orange. So the sum of these probabilities, P orange, will equal 1. Oh, I'll need a common denominator here, so we can say this is 4/12, this is 3/12, and this is some other amount. Again, we're trying to find our probability of orange. So I could subtract 7/12 from 1. The probability that we get an orange marble is going to be 1 minus 7/12, or 5 over 12. We know that there are 3 different events, all of whose probability will add up to 1. To find the probability of orange, we simply subtract the probability of the other 2 options happening. So in your notes, I believe you have a image of a deck of cards. We found that in the last few years that not everyone knows exactly all the same language when it comes to playing cards. Playing cards go from 1 to 10, and then there are 3 face cards: a jack, a queen, and a king. There are 4 suits: clubs, diamonds, hearts, and spades. I'll try to talk through that as we look at these problems and try to make sense of what's going on here. So in a standard 52 card deck, there are half are black and half are red. So in other words, the probability that pulling a card, well, there's 26 black cards, 13 clubs and 13 spades, out of a total of 52 cards, or 1 out of 2. If we wanted to calculate the probability that we have a face card, well, there's 3 in each of the 4 suits. There are 12 total face cards out of 52, and we can simplify that fraction down to 3 over 13. On example C, we're asking for the probability that the card is an ace. Well, there's 4 aces out of the 52 cards in the deck, or 1 out of 13. Part D, we're asking to find the probability that we get a 3, a 4, a 5, a 6, or a 7, meaning inclusive means 3 and 7 are included. So there's 4 threes, so there's 4 threes, 4 fours, 4 fives, 4 sixes, and 4 sevens. That's a total of 20 out of the total 52 cards, which we could simplify down to 5 out of 13. Example E asks us to find the probability that the card is the 8 of clubs. There's only 1 out of the total 52 cards. That will be our probability. And then we get into example F, find the probability of drawing a queen and another queen. Now, this idea of with replacement means that I pull a queen and then put that card back into the deck. So the probability of getting a queen would be 1 out of 13 times 1 out of 13 for a total probability of 1 out of 169. Now, without replacement means I'm going to pull a queen out of the deck, whose probability will be 1 out of 13. And then I keep that card out of the deck. The odds have changed. I only have 3 queens in the deck remaining out of a total of 51 cards. Well, that fraction is simplifiable. We can multiply 1/13 times 1/17 for a true probability of 1 out of 221. I think you guys should pause here and try the next 4 examples on your own, 3, 4, 5, and 6. Once we get past 6, we turn into some more experimental probability, rather than our theoretical. So I'd like you to try these 4. I'll work them out as usual, and you can check in to see how you did. Let's see how it goes. On number 3, they tell us that a die is rolled. Find the probability of getting a number greater than 4. Well, that's the probability of getting either a 5 or a 6. So there's 2 out of 6 total options. Our probability would be 1/3. On number 4, they are asking us the probability of getting a sum of 5 when 2 dice are rolled. So I think the easier way to think about this is if we think about the dice as having different colors. Right? You can see here I have blue and red highlighting my numbers. The way I could get a 5 is I could roll a 1, a 2, a 3, or a 4 with my blue dice, and a 4, a 3, a 2, and a 1, respectively, with the red dice. Those represent 4 of the different outcomes that we would be desiring here, out of a total of 36 outcomes. Understanding that 6 times 6 are the total number of outcomes we could get. 4 of those are the desired, so our probability would be 1 out of 9. In example 5, Florida's lottery game is set up so that each player chooses 6 different numbers, 1 to 53. If the 6 numbers match exactly, the top prize is 1, and it's several $1 million. Yay, yay. With 1 lotto ticket, what is the probability of winning the top prize? Well, if we're picking 6 different numbers, I have to choose the first number exactly right. I have a 1 out of 53 chance. If I get that first number right, I know the second one must be different, so now it's 1 out of 52. The third, 1 out of 51, 150, 1 out of 50, 1 out of 49, and 1 out of 48. The likelihood of getting those 6 numbers exactly right is extremely small. 1 out of 1.65 times 10 to the 10th was what I got for this particular problem. Finally, example 6, a family has 5 boys. Find the probability of this occurrence. We're assuming here that there's 2 outcomes, the gender of your birth, male and female, boy and girl. That probability of getting a boy would be 1 out of 2, repeated 5 times. So 1 out of 2 times 1/2 times 1/2 times 1/2 ends us with 1 out of 32. So let's look at these experimental probability problems, 7, 8, and 9. I think I'll work through the first one, number 7, the multi-part, and then let you try 8 and 9 on your own. Here on number 7, they tell us that when women turn 40, gynecologists typically recommend they get a mammogram. The table shows us information based on women ages 40 to 50 who had a mammogram or not, a positive or negative mammogram, and whether or not they had breast cancer or not. So in part A, they want us to find the probability that a woman aged 40 to 50 has a positive mammogram. Well, that is going to be all of these entries in this column, in this row rather, 720 plus 6,944. So that's a total of 7,664 out of 100,000 for a probability of 7.664%. Part B, among women with breast cancer, what that means is we're really only limited to this set of data. Among women with breast cancer, find the probability of a positive mammogram. Well, that's going to be 720 out of 800, which we can also think of as 90% or 9/10. Our denominator is different there because of this statement, among women with breast cancer. We've limited our sample set to account for a different set of a different type of question. On part C, they ask us among women with positive mammograms, let's use a different color here, among this group, among women with positive mammograms, find the probability of having breast cancer. Well, that is going to be 720 out of 7,664 for a probability of 9.39%. So these type of questions, they can be confusing, right? We need to always think about what is the outcome we are looking for and the total sample, the total number of people in that group. All right, I know this video is getting long. We got 2 more examples to work through. You're going to try those on your own, and I'll share my work with you in just a minute. Sorry about that. I was thinking, I think I had an older copy of the notes I was working off of. Let's just look at number 8, and we'll wrap up here. Here they tell us that we have a table of information representing the marital status of U.S. population ages 15 or older in 2010. So first, I want us to find the probability that one person is divorced and male. Well, we have a category for that, right? This divorced male is this cell here. That represents 10 out of the total of 242 people in the selected group. So that is our probability. We could simplify that fraction to 5 out of 121 if we had to. In part B, we are looking to find the probability that one randomly selected person is married or divorced. So married or divorced. So we have 130 plus 24 out of the total 242. These are mutually exclusive. We can't be both married and divorced. If we're divorced, we're no longer married. So that's why we can add these probabilities together. That wraps up our lesson on probability. Thanks, everybody, for your time.